Then the other one is the distance perpendicular to the clearance space. Okay, so I'm going to move my element a bit, okay, just slightly. Then after that, I'm going to sketch the velocity profile. Okay, so the velocity profile looks like this. The longer the arrow means the higher the velocity. Okay, so you can realize that at the interface, at the two chip interface, right, the velocity slow down. Why? Because it's closer to a contacting surface. So this is what we call VC, okay, chip velocity. Over here, right, it goes this way. The longer the arrow means the faster the velocity. So this is going through your velocity U, which is your cutting speed. Okay, which is your cutting speed. Right. So now, how will the element deform? Right? How will the element deform? So I'm going to sketch how the element will deform. So the element on the rake face will deform this way. The element on the clearance face will deform this way. Okay. So now I will quickly make you recall. Okay, so I'm going to write distance down here. I need space. So I'll quickly recall what do we mean by positive shear. So if we have a positive shear, right? If this is our element, right? This is our element. So this is positive shear, right? So the element will deform this way. Okay. And then if we have negative shear, all right, the element will deform this way. Okay, so that's what. So if you look at our elements now, okay, when you look at the element, you have to orientate your head or your eyesight such that you are looking element one like reading it upright. Okay, so what do I mean? So if you look at element one, right, the deformation is doing this. And then if you look at element two, the deformation is doing this way. So can anyone tell me element one, is it positive or negative shear?
Negative.
Well done. So what you see down here, right? Element one and over here it looks the same, right? So the element one is going through what? Negative shear. And then if you look at element two, right? If you look at element two, if you have to focus in this region over here, right? And you see this is also the same, right? So this is positive shear. So the shear on the chip, so this is my chip, is going through negative shear, and on my clearance space is going through what? Positive shear. So now we're going to sketch the shear stress distribution. Now we're going to sketch our shear stress distribution. Okay. One thing I want you to take note is why the deformation at this point, right? At this point, travels so much further because our velocity furthest away from the what? Furthest away from the contacting surface is the fastest. Okay, so that's why you have this sort of deformation. Now, so I'm going to name. Okay, so this is my point A. Right over here, this is my point B, right? Then over here, this is my point C. Okay, I'm going to label 3 points, A, B, and C. So if we were to draw the distribution of the shear stress, right? So we have one axis over here, right? This is my distance. Y-axis is my shear. Okay, so on top is positive, below is negative. Okay, this is not Mohs circle. Okay, we apply Mohs circle only up to here. Okay, this is distance. Okay, and positive, negative shear, nothing to do with normal stress. Okay, so this is my point A. At the center over here is our point B, and this is our point C. Right. So at point A we have negative shear. Right. At point A, so we have negative shear. At point B or point C onwards, we have positive shear. So I'm going to sketch now. Okay, we are going to sketch the shear stress distribution. Right, so we're going to have this. Right, and then we're going to have positive. Now at B, what will happen is this. Okay, from negative to positive, you have to pass through B. Okay, or not, there's no continuity. There's no continuity. The physics don't make sense. Okay, so it has to pass through B. And at B, the shear stress is equal to what? 0. Okay. So when the shear stress is equal to 0, why it has to pass through 0? Because point A, we define point A will have negative shear. Point C has to have what? Positive shear. Right? So when you go through B, right, where the material is stagnated, right, the velocity V is also equal to what? 0. So when the velocity is equal to the 0, that's where we got the what? We call it stagnation region. Right? That's where when we saw when we saw the video, right? When we sorry, what did I do now? Okay, when we saw the video, I'll string down. Hey, sorry. So that's when we do the seriously, Eugene. Right, when we saw the video over here, right? Right, the stagnation zone is there because one side is going to what? Positive shear, the other side is going to negative shear. So positive going negative going to positive, it has to go to what? 0. So that's why you have a stagnated region. So everything goes back to what? This is in fact solid mechanics. Okay, what I'm introducing you is solid mechanics now. By using Mohs circle, but you can explain the phenomena why is the stagnation zone exists. Okay, this is a typical question I ask when people want to do PhD with me. This is a typical question that I ask. Okay, so I have a lot of applicants from all over the world to want to do PhD with me, and I ask them simple questions like this, and it's so sad. Okay, even for this case, this is a different material. Now we can see you still get what? Stagnated zone. You still get the stagnated region. Okay, and you know, the future of our engineering career is adaptability and multidisciplinary. I know we're going to a manufacturing course. You guys were thinking, Eugene, this is a manufacturing course. Why the hell am I doing Mohs circle? No doubt it's manufacturing, but we still incorporate what? Material science, engineering, mechanics, physics. Yes or no? It's still important. Okay, right. So let's look at now. I think this is enough on mechanics. Okay. So let's look at process parameter. Okay, let's look at process parameter now. So I'm going to get rid of this region first. Okay, let's look at process parameter. Like,
Professor,
yes.
is B at the origin of that little graph that you made there?
Yep.
Thanks.
You got it there. You understand the graph. So on the x-axis is the distance, okay? It's just a normalized distance. There's no x and y. It's just a magnitude, okay? That's why you guys will be wondering.
Professor,
Yep.
it also looks like you wrote shear equals 0 when shear equals 0 on the graph. Is that
Yeah.
supposed to be distance?
Yeah. No. When I wrote this, shear is equal to 0. When okay. Okay.
Is that supposed to be distance?
No. When shear is equal to 0. I wrote
Okay.
twice.
All right, thank you.
Thank you. Right. So let's look at process parameter. Okay, let's look at process parameter. So in metal cutting, okay, metal cutting, the process parameter are as follows. Okay, so what are they? So you have 1, cutting speed, feed rate or undeformed chip thickness, we have depth of cut, or sometimes we call it width of cut. I know it's confusing, right? I just say depth of cut. Sometimes we also call it width of cut. Then we have rake angle. Okay, so rake angle. Then we also have things like what is the cutting edge radius. Okay, cutting nose radius. Both are two different things. Okay, then we also look at rake angle. We wrote that. Then we also have things like cutter path. Which I will explain later, or how the tool is moving. Okay, cutting environment. Okay, so if you look at the number of parameters, okay, 2, 3, 4, 5, 6, you have about 8. All right, 1, 2, 3, 4, 5, 6. So sometimes we also have approach angle. Okay, you have so many variables. Okay, you have so many variables, and let's say if this material is very new, you have not a clue how to process this material. And if we were like a typical mechanical engineer will do a 3-level full factorial test, we have to carry out 729 tests, which is ridiculous. Okay, which is absolutely ridiculous and a waste of time. Okay, so these are the process parameter first. Okay, now I'm going to custom all this into turning first. Let's look into turning, okay? Then we're going to describe how we can set these values, okay? What is a very first intelligent guess on all these values. And this is, the intelligent guess is possible through material mechanical behavior. You guys say, holy crap, freaking Johnson Cook again. Yes, okay? Oh, here we go again, Eugene. Come on, give us a break. It is, okay? all depends on the mechanical behavior of now a combination of the tool and a combination on the workpiece. Okay, not just one thing. Okay. So I'm going to help you because